Swayam Prabha. Digital India. Educated India.
Hello everyone, this is Dr. Vishal Trivedi from Department of Biosciences and Bioengineering, IIT Guwahati. And what we were discussing about the different properties of the enzyme in the course Enzyme Science and Technology. And in this context, in the current module, we are discussing about the different ways in which you can be able to measure the enzyme activity. So if you recall, in the previous lecture, we have discussed about the different aspects and how on different types of assays what you can actually be able to set up to measure the enzyme activity. Now, when you talk about the enzyme activity, you are actually going to talk about the several types of enzyme catalyzed reactions. These enzyme catalyzed reaction could belong to the catabolic reactions or the anabolic reactions. So anabolic reactions are the reactions which are going to be used for synthesizing the new molecule, whereas the catabolic reactions are the reactions which are where the biomolecule is going to be broken down or oxidized to generate the energy. Now, when we talk about the enzyme activity, this means we are actually going to talk about that the enzyme is actually processing the substrate, and in that process the enzyme is actually going to generate the product. Okay, and if you want to measure the enzyme activity, and if you recall in our previous lecture we have discussed what are different ways in which you can be able to express the enzyme activity. So one of the classical way of expressing the enzyme activity is that you are going to express the enzyme activity in the units, right? And every unit is actually going to be defined as the amount of enzyme required to convert a 1 micromole of substrate into the product in a given time or 1 minute. And this we can calculate. So enzyme activity can be calculated if we can be able to measure the consumption of substrate or the production of the product, right? Now, if I want to measure the substrate or the product, I could actually be able to use the exclusive property associated with this particular substrate or exclusive properties associated with the product, right? So in that case, so in many cases, we can actually be able to see the disappearance of the substrate. In some cases, you can be able to see the appearance of the product, right? When you see the appearance of the product, it is actually going to give you the positive signal. Okay, so this is actually going to give you the positive signal, which means you are actually going to see a increase in some value, right? So it is actually going to give you a positive signal. Whereas when you are going to see a disappearance of the substrate, then it is actually going to give you the negative signal, right? What is mean by the negative signal is that your starting molecule, for example, if you started with 100 molecules of substrate, then so at time 0, for example, right, at time 0 you have started with 100 molecules of substrate, right? After 10 minutes it is actually going to be 80, right? So suppose 100 molecules of and suppose we are measuring the absorbance of this particular substrate, right? And this is actually exclusive, right? So and does not have the any kind of cross reactivity from the product or the enzyme. Then, for example, if you have the absorbance of this 100 molecule as 0.8, for example, then 80 molecule will actually going to show you an absorbance of 0.6 After 20 minutes, you are going to have an absorbance of 60, 40, like that, and ultimately it is going to be 0, right? So similarly, you can actually be going to have a decrease in absorbance, right? This means you are actually going to know what is the amount of substrate going to be consumed if you are actually, so you started with 100 molecules, now you have 80 molecules, right? So you can actually be able to take this value and you will say, okay, zero point 0.2 OD substrate is being consumed in 10 minutes, and that is the way you can be able to use these values to calculate the enzyme activity. Similarly, when you are going to talk about the positive signal, you are actually going to say that same way, right? You can have the time, you can actually be able to say at the starting you are going to have 0 molecules and you are going to have 0 absorbance. So it's actually going to say absorbance, number of product molecules, right? And like that. Okay, so time 0, you're going to start, there will be no product form, right? Because the enzyme has just started the reactions, and then absorbance is also going to be 0, right? Then after 10 minutes, you are actually going to see 20 molecules, right? This is not exactly what is happening there, right? 20 molecules are going to be consumed, right? So 20 molecules are going to be produced, right? So 20 molecules are going to show you an OD of suppose 0.35, okay? Similarly, you can have 20, 30 like that, and it is actually going to show you 30 molecules, 40 molecules like that. So it's going to show you an absorbance of 0.5, and it's going to show you an absorbance of 0.7 something. So this is actually the direct measurement, right? Here you are actually going to plot this. So 0.35 is the concentration of the substrate product, right? And you can actually be able to say that this is amount of the product is being formed, and that's why this is the same amount of substrate is being consumed, so that you can actually be able to use for calculating the enzyme. So that's why you see when you are measuring the product, it is easy and straightforward, whereas when you are measuring the substrate, you are actually going to go through with the another function, right? You have to always calculate the delta absorbance, right? You have to calculate how much absorbance is gone down, right? So in this case, 0.8 to 0.6, then for example, here from here to here, again 0.2, from here to here, it's going to be 0.1 like that. So here you have additional step, and when you have the additional step, more steps means you are actually going to increase the number of chances of incorporating the errors. And that's why it is advisable to go with the positive signal rather than the negative signal, or I will say you should not measure the disappearance of the substrate, rather than you can actually be able to measure the appearance of the product. So depending on the different types of properties of the substrate or the product, the enzyme assays can be done by the utilizing the different types of techniques. What are these techniques? You can actually be able to use the photometric assays. So you can actually be able to use the photometric assays where you can actually be able to change in absorbance, or you can actually be able to change in the fluorescence, and you can actually be able to say luminescence and all that. And then you can also have the radiometric assays. So these radiometric assays where you are going to see the change in the radioactivity of the substrate or the product. And then you can also have the chromatographic techniques, which you can also use for measuring the enzyme assays. And here you can actually be able to capture the substrate or the product, right? And you can actually be able to measure that with the help of either the radiometric assays or the photometric assays. And then you can also have the gel electrophoresis. So you can actually be able to visualize the product onto the electrophoretic gel, and that you can also be able to use for measuring the enzyme activity or enzyme assays. So enzyme assay is a very complicated recipe, or I will say enzyme assay is a complicated protocol where you are going to use not only one type of assay. You may have the possibility of using the multiple combinations of different types of techniques. For example, you can actually be able to use the chromatography techniques to isolate the product, right? And you can actually be able to use this product, and you can actually be able to quantitate this product with the help of either the photometric assays or radiometric assays. Same way, you can actually be able to use the electrophoretic assays or electrophoretic system to visualize the substrate, and then you can actually be able to use either the photometric assays or radiometric assays to quantitate the product, right? So let's start first with the photometric assays, and we'll discuss different aspects of photometric assays, how you can be able to, what are the different precautions you should take when you are setting up the photometric assays, and when we'll discuss about the UV visible spectroscopy and as well as the fluorescence spectroscopy, how you can be able to exploit these techniques for setting up a fluorometric assays and photometric assays, and how you can be able to utilize that for measuring the enzyme activity. So photometric assays, as the name suggests, photometric assays means you are actually going to absorb, or you are actually going to see something with related to light, right? Photometric means, photo means light, metric means measuring, right? So you are actually going to do the light measurements, whether the light is going to be absorbed by the substrate, right, or product, or it is actually going to be that the substrate or the product is actually going to produce the light, right? Sometimes you can actually have to, we'll be able to see that if there is a product which is formed, it is actually, giving the light, right? Or sometimes you can actually have the alternative, right, where you are going to excite the molecules, and then it is actually going to give you the fluorescence, right? So fluorescence is also a phenomena where you are actually going to measure the light intensity only. Okay, so let's discuss and start discussing about the photometric assays. So as the name suggests, the photometric assays are the most commonly used type of enzyme assays. They are convenient and capable of producing the accurate and reproducible result on large number of samples in a short period of time. So photometric assays are the most popular and most important, and it is easy to perform, and in terms of infrastructure, in terms of instruments, in terms of the reagents, they all are very much cheap actually, so it's economically very viable. The chemical transformations that accompany the enzyme catalyzed conversion of substrate to product frequently results in a useful change in the optical property of the system under the investigation. So either there will be a change in the substrate absorbance, or there will be a change in the product absorbance. Okay, so either you can have a very exclusive product which actually can give you the exclusive the light absorption phenomena, or you can actually have a substrate which is going to show your disappearance. When the reaction is catalyzed by the enzyme under assay do not produce a useful change in optical property, the addition of the appropriate additional reagent frequently allow the reaction to be photometrically monitored. So these are actually going to be a couple of examples where neither the substrate nor the product are exclusive. Then you can actually be able to add some coloring agent, and that coloring agent is going to either react with substrate or the product, and then ultimately it is actually going to give you the color change actually, and that's you can actually be able to monitor with the help of the photometric systems. The other photometric methods are less commonly used than enzyme assay based on change in light absorbed by the solution as the reaction processes. Change in the fluorescence and the turbidity of the solution, on the other hand, provide the foundations for useful optical method for assaying the enzyme. So before we discuss and understand the phenomena of the photometric assays and how you can be able to design the assays, let's discuss some basics of the photometry and how it actually works. So first thing what we have to discuss is we have to discuss about the absorption phenomena. So what you know is this is actually the UV visible spectra, right? And what you see is this is the radiation of the different wavelengths, right? So you started from the radio waves. You can actually be able to talk about microwaves. Then you have infrareds, and on this side you have the ultraviolet, X-ray, and gamma, right? So as you go from this side to this side, there will be decrease in wavelength, and that's how there will be an increase in intensity. And this is the region which is called as the visible light, or this is going to start from the from somewhere around 400 nanometer to 700 nanometer, right? So that is will be the called as the UV visible spectroscopy. And next to the 400 nanometer, it's go up to the 250 nanometer, or sometime it's going to be 190 nanometer, and that is going to be called as UV range. Okay, so UV region also can be used for photometric assays. So you can actually have the UV visible range of the spectrum, and that can be used for the all the photometric set assays. So visible light is of wavelength between the 400 to 750 nanometer. Compounds that absorb light in this range are colored. Many colorless compounds also absorb light in the UV range, that is from the 200 to 400 nanometers. And light absorption occur when the electron in a irradiated absorbing molecules are promoted to a high energy level, because the frequency of the electronic oscillation in the molecule coincide with the frequency of the irradiating lights. The wavelength of this frequency is that at which compound absorb maximum amount of light is depend on the structure of that particular molecule. The amount of light absorbed depend on the probability that the electronic collision occurs. And if you recall in our in a couple of module back, when we were discussing about the the different types of UV visible spectroscopy, we discussed about that when we were saying that how you can be able to use the spectroscopy for measuring the enzyme substrate interaction, right? That time we discussed about how the absorption is changed even if when you have a slight modification of one group, or there is a substitution of the few more groups, right? So remember that when we were talking about how the absorption phenomena is changing when the benzene is getting benzene is getting substituted at different unit values, and so on. Second thing what we have to discuss is about the absorbance. So absorbance is A is equal to minus log I by I0, and where I0 is the light transmitted by the solution not containing the chromophore, right? So it is I0 is the light transmitted by the solution not containing the chromophore, which means that this is, and the I is a light transmitted by the solution that does contain the chromophore, okay? And A is the absorbance. So A is actually a ratio of I by I0, and because this is a ratio, it does not have any unit, because so that is very important, right? Many times even in the different types of exams, they will actually going to ask what will be the unit of absorbance. So it is a unitless property. How you can convert the absorbance to the concentrations, right? So absorbance is directly proportional to the concentration, right? So if you recall from the Beers-Lambert law, what Beers-Lambert law is says that absorbance is directly proportional to the concentration, and absorbance is also directly proportional to the path length, which means if you combine these two, absorbance is going to be equal to the epsilon CL, right? And epsilon is called as the molar absorption coefficient, and unit is mole per centimeter, right? So if you keep the path length constant, right? If you keep the path length constant, then the absorbance, then the concentration is going to be the absorbance divided by the epsilon, okay? So when the path length of the cuvette or path length of the light path is 1 centimeter, it is going to be constant, right? So if it is a constant event, we can actually be able to ignore this, right? And that's how the amount of, as you will increase the concentration, there will be an increase in absorbance, and you can actually be able to calculate the concentration of the molecule with the help of the absorbance divided by epsilon, okay? This means if you can have the molar absorption coefficient of the molecule, you can take the defined, you can take the molecules, put it into the cuvette, and then if you measure the values, right, if you measure the absorbance, and then you can actually be able to just divide that value by the molar absorption coefficient, it will actually going to tell you what will be the concentration in terms of moles, right? And that is it's a very, very, powerful tool, right, to measure, right? There are deviations from the Beer-Lambert law, and that we are not going to discuss here because there are saturations, and then there will be a product dimerizations and defragmentations and all that. So that is actually going to change the this particular relationship, but that is called as the deviation from the Beer-Lambert law, and that you can actually be able to study from any of the classical biochemistry book that or biophysics books. Like I think the if you go through with the book Wilson and Golding, right? So if you think about this, right, you can actually be able to know this, right? So you can actually be able to study about the deviation from the Beer-Lambert law, and that is going to be helpful to understand under what conditions the law will not be applicable, and then we should be little more careful. Okay. Now let's talk about the instrumentation part. So instrumentation of the spectrophotometer. So all photometric instruments operated by the same basic principles. Light from a light source of a specific wavelength is passed to the cuvette containing solution of our interest, right, molecule, for which you want to measure the absorbance, which is then detected by the photometric detector, right? So what you see here is you are going to have a light source. Then in front of this light source, you are going to have the monochromators. So monochromator is nothing but a prism, right? So it's going to have a prism. And you know that when the light goes through the prism, it actually diffract, and that's how it is actually going to show you the different wavelength, right? And remember that when the white light goes into the prism, it actually going to split into different 7 color, right? And since it got fragmented into 7 color, you can actually be able to rotate this prism, and that's how you can be able to select the wavelength of your choice. So same is here. You can actually be able to rotate this, and that's how your wavelength of your choice will enter into this particular slit, right? The slit will be a small gap between or the hole, and from there you can actually be able to allow the entry of this particular array, right? And then there will be a place where you can actually be able to keep the cuvette, and that's how the cuvette is actually going to have the molecule, right, for which you want to measure the absorbance, and that's how uh, the unabsorbed light will actually going to pass through the cuvette, and it is actually going to be detected by the detector. And detector could be of many types. It could be photodiodes or photomultipliers. The wavelength of the absorption for different chromophore is different, right? And therefore, it is essential to restrict the wavelength of light source before the chromophore is exposed to it. Now, we will discuss about the different components. So, first component is the light source, right? The selection of the light source is predominantly depend on the wavelength in which the measurement are to be made. So, either the UV visible or UV range or the visible range. The most used light source for the glass enveloped filament tube bulb, the quartz enveloped tungsten halogen bulb, or the deuterium lamp, and more recently the xenon lamp. So many of these lamps are available. You can actually use the tungsten lamp, or you can use the halogen lamp, you can use the deuterium lamp, and you can also use the xenon lamp. And all they are actually capable of providing the light of the different wavelengths, so that you can actually be able to use according to your choice. And sometimes what happens is that in some of these spectrophotometer, you may have the 2 lamps rather than single lamp, right? So you can have the lamp for the visible range, you can have the lamp for the UV range. To cover the useful UV visible range, that is from 200 to 700 nanometer, an instrument using both deuterium and the quartz halogen lamp is usually necessary, although diode array instrument rely on a single. So low pressure deuterium lamp that emits sufficient light over the whole UV visible range. Okay, so you have the choice. You can actually be able to use the 2 lamps. You can actually be able to use the single lamp. Then we have the wavelength selector. So this is called as the diffraction gratings, right, or the prisms, right. So the reliability of the absorbance values will highly depend on the accuracy of the wavelength to which the chromophore is exposed. That is the specific wavelength, right. So selection of the lambda is very important, right. And that's why the wavelength selector is a very, very important component of the spectrophotometer. The colorimetric simply use a series of filters to filter out all the wavelength other than that of a required specific wavelength. But the availability of range filter is very small, and sometimes the wavelength to which the chromophore is exposed is a well away from its normal lambda max values. Okay, so there are many ways in which you can be able to use the wavelength selectors. You can have the filters, you can have the diffraction gratings, you can have the prisms, right? So depending on the price of the instrument, you can actually have the different types of things, right? And that's how you can actually be able to have the precision in terms of selecting the particular wavelength. And if you are going to have multiple wavelengths, it's actually going to affect the final absorbance phenomena. The modern spectrophotometer uses a holographic diffraction grating to disperse the light from the source into a spectrum. Rotation of the diffraction grating varies the light wavelength of the emergent light passing through a slit, and to extent to which this approximate to a monochromatic light depend on the wavelength of the slit, and it is described in the specification of the instrument as the bandwidth. So bandwidth is the deviation from the selected wavelength. Okay. Then you have the determination of the absorption spectra. So many photometric enzyme assay problems can be solved more quickly if the absorption spectra of a solution involved can be determined rapidly. This can only be accomplished in an instrument that uses physical movement of the diffraction grating to irradiate the sample with the monochromatic lights. This means you can actually be able to absorb, you can actually be able to have the absorption spectra of the molecule, right? So you can actually have like lambda on this side and absorbance on this side, and that's how you can actually be able to know where this particular molecule is absorbing, and that's how you can actually